Okay, in this video we're going to have a look at gravitational potential energy, which is sometimes also just referred to as potential energy, although technically the term potential energy could include a couple of other types of energy too. Anyway, let's have a look. Just before we get into that, we should probably start with looking at what does that term energy mean. So energy, the definition is energy is the capacity to do work. Now we're going to look at the physics definition in science, or the scientific definition for work in another couple of sort of episodes, so a little bit later. But energy is the capacity to do work. Now work, strictly speaking, is a force applied through a distance. So it means energy is the capacity to apply a force. But really you can probably just think of this as energy is what's needed to make anything happen. So to make anything move or to light anything up, if you think of all the different types of energy, whenever anything happens, energy is involved. So this may be a definition you need to learn, and we'll look more at what this term work is later, but energy is the capacity to do work. Alright, so we're going to look specifically at a type of energy in this video called gravitational potential energy. So let's just have a look at what does that term mean? Well, we've got the term gravitational here, as you know, the hint there, it's got to do with gravity. Potential literally just means stored. It's a stored form of energy. So this is the form of energy that anything has that's above the ground. So a plane in the air or a ball that's been thrown into the air, anything that's above the ground has gravitational potential energy stored in it. So if we look at an object that's above the ground, so if we pretend I've got a ball here and it's a certain height above the ground. Sorry, my arrow's a bit wonky there. Alright, my ball's a bit wonky too. Let's just, there we go. Alright. Okay, so we've got a ball above the ground here. If we look at, it's got a form of stored energy, and you can imagine someone might be holding the ball, and if it's dropped, then suddenly that energy would change into kinetic or moving energy. So this ball that's above the ground has a stored form of energy we call gravitational potential energy. Now, what factors contribute to gravitational potential energy? Well, the potential energy, gravitational potential energy, we do E for energy, and often a little P for potential, or sometimes I've even seen people do a little GPE, gravitational potential energy, is equal to M times G times H. So what are these three things? Well, the first thing is the mass. Now you could imagine, imagine if you were lying down here, and I was going to drop this ball onto you. So when it hits you, the amount of energy it hits you with will be proportionate to the amount of gravitational potential energy it had to begin with up here. So you could imagine it's going to hit you with a whole lot more force. It's going to have more energy if the ball is heavier. So we might have a ball here that's 1 kg. If you've got medicine balls, or it could even be a ball that's 10 kg, some of those big rubber heavy medicine balls. And I remember I actually had a friend when I was in high school, and when we had gym class, drop one of these really heavy medicine balls on a friend on his stomach, and he actually had to, after that, go change his shorts afterwards. But anyway, that aside, the mass of the object will affect how much stored gravitational potential energy it has up here. The other thing is the amount of gravity. So G here is the amount of gravity, and that's actually an acceleration value, or we can look at it as a force due to gravity. So gravity, in a previous one of my previous episodes, we said we often just simplify that or round it to, we use the value 10. So on Earth we often use the value 10 for gravity. It's actually more like 9.8 something. Now the last factor, so you could imagine like on the moon this value would be smaller, so on the moon this object would, under the same conditions would have less energy, and out in space, well, it's not going to have any gravitational potential energy. So the last one is height. So the amount of height above the object, above the ground, is going to determine how much gravitational potential energy it has as well. So obviously if I hold the ball up a lot higher and let it go, it's going to hit you a lot harder. If we hold it down lower, it's not going to hit you as hard either. So the amount of gravitational potential energy, the stored form of energy an object has, is proportionate to its mass, the amount of gravity, and the height above the ground. So in this case, we could say our gravitational potential energy, let's say it's a meter off the ground, and let's say it's a really heavy one, a really heavy medicine ball, it's 10 kgs. Alright, so we could say in this case, and we'll use a different colour here, we could say our potential energy, our gravitational potential energy here is 10 kgs. That's going to be times 10 for gravity, and times 1 meter, alright, the height. So this would be 100. It would have 100 joules of energy stored up the top here. It would have 100 joules of energy. So the unit that we use to measure energy is always joules, and it's a capital J is the symbol used. So trying to make sure you don't do a lowercase j. And that's just a unit, just like if we're measuring distance, we use meters, or time, we use seconds. Joules is how we quantify or how we measure the amount of energy something has. So up here, the ball has 100 joules. Now, we can use this formula, and we can actually rearrange it slightly as well. So you can see I've given you the triangle. So in your exam, it'll be given to you on the front page, most likely in this format. So it'll probably be EP equals mgh, so mass times gravity times height. Sometimes they put a little triangle in front of the h to show you it's a change in height. So if it, if it's how high it is above the ground or above the surface, so it might be a change in height. But essentially your formula is going to look something like this. So we can put that into a triangle, and you remember I said if we put one of these formulas into a triangle, well, essentially, if there isn't a value on top, we can put the first value that's here in the top of the triangle. So we've got the energy potential here, and mass times gravity times height down the bottom here. So we can arrange this if we wanted to work out the mass. If we wanted to work out mass, it would be, so I'm trying to work out the mass here. So I cover that one up with my finger, and what do I get? It's the energy, the potential energy, divided by, and it'll be gravity times height underneath there. And so I'll put that in brackets because we'd have to times those together first before we do energy divided by that value. Alright, so if we wanted, let me just clear that. If we wanted to work out the gravity, so if we wanted G, we could go G equals, and again it's the potential energy on top divided by, in this case it'll be mass times height. So the other two are underneath. And if we wanted the height, we could take the potential energy divided by mass times gravity. Okay, so it's just a rearranging of this triangle here. Now some of you who are pretty good at maths, you could rearrange it without using the triangle. For instance, if I want to get gravity and height over this side, then I divide by gravity times height on this side. You can see that's what we've done over here. So if your algebra is good enough, you should be able to arrange it anyway. But some of you might find it helpful, at least at, especially at year 11, to use these triangles. So whichever value you want, you cover that up with your finger. So if we wanted gravity here, for instance, we cover that up, and it's going to be energy divided by the mass times height. So we times the mass times height, and energy divided by that. So hopefully that makes some sense. That's how we can rearrange it. And we're going to look at a few problems where we have to apply this just a little bit later. We're going to do a little basic one right now, and in one of my next videos we'll do a slightly more complicated problem. So if we have a look here, a girl of mass 60 kgs. So what I like to do if I get a problem like this is I write down what I've been given. So I go, I've been given a mass equals 60 kgs, uses 5,100 joules of energy when she climbs a vertical rope. So I've been given an energy. So the energy in this case is 5,100 joules when she climbs a vertical rope. Calculate the maximum height it would be possible for the girl to reach. So I need to work out the height. So the height is my unknown one that I need to figure out. So already I could look at this and I could look at the formula I've been given and try and work out, how could I figure out the height here. So in this case we could take the energy, right, the potential energy equals mass times gravity times height. And if we want, we could use the triangle version. So we've got the energy in the top there, and underneath here it's the mass, gravity and height. So if we rearrange this, we can get height is equal to the energy divided by the mass times gravity. So what is that? Okay, well we take out 5,100, our joules, our energy, and we divide that by, down the bottom here, and I'll put it in some brackets, we've got 60 times, now what's gravity? The mass is 60, but what's gravity? Well, that's a value, it wasn't given to you in the question here, but it would actually be on the front page with your formula. Somewhere there it will say G equals 10 newtons per kilogram or something like that. So it'll give you the value for gravity as always on the front page, and for this curriculum or at year 11 we assume it's 10. Like I said, it's actually 9.8 something, but in year 11 science we just round to, we assume it's 10. So if we do that, we can work that out. It's going to be 5,100 divided by 600, which, if I chuck that in my calculator, is going to be equal to 5,100 is going to be equal to 8.5, 8.5, and it's meters. It's a height, it's a measure of distance, so in this case it's 8.5 meters. Okay, so looking at this formula, just going through that again, E is for energy, and that's measured in joules, M is the mass, so that's kilograms, G for gravity, and the unit for that is newtons per kg, or it can actually be meters per second. I wouldn't worry too much about that one. Whenever you see the G, just use the value 10. And the H there, the height, is obviously a distance, so that's measured in meters as our standard measure for distance. So hopefully that made sense. You can always flick back and watch again, but we're going to leave it there, and we're going to look at now kinetic energy in the next video, and then we'll do a more complicated problem that actually involves both kinetic energy and gravitational potential energy.